In the previous video, we looked at the derivative of essentially power functions, x to a power, and saw that this was n times x to the n minus 1. The proof that we gave was only for positive integer values of n, but it turns out that this works for whether n is positive or negative or whatnot, or even rational or irrational. This still works. I want to extend this to general polynomials, and general polynomials are essentially sums of different powers of n. So I need a couple of properties here that'll help me do this. Properties of derivatives. And the first property is that the derivative of a constant times a function is the constant times the derivative. Right? Think about this graphically, that if I've got, the graph of a function, right? So this is y equals f of x, and then I think about what is the graph of k, y equals k times f of x. What does multiplying the function by a constant do? Well, multiplying the function by a constant scales the function up by a factor of k. It doesn't change anything horizontally, it just changes it vertically. So if I'm thinking in terms of slopes, if I'm looking at a slope here or a slope there, well, I haven't changed any runs. I haven't changed anything in the x direction. I've only multiplied the y value by a factor of k. So where this used to be, let's say, 1, this is now k. If this height was 2, this is now 2 times k. If this was 3, this is 3 times k. That the rises, the runs didn't change, but the rises get multiplied by k. Why? I can't remember. This was k times f of x, k times f of x. The point is, it was the same. You take x, you figure out what the function value is, and here you multiply by k. So I've got these taller, I'm thinking of k is bigger than 1, but you're stretching in the y direction by a factor of k. So when I look at this rise divided by run versus that rise divided by run, it's the same run. This rise is k times as big as that one, and so this slope is k times as big as this one. And that's what this property is saying. Okay. Now, that's my first property. My second property is this, that the derivative of a sum of two functions, f of x plus g of x, is the derivative of, the derivative of the sum is the sum of the derivatives. So take the derivative of f of x, take the derivative of g of x, and add them together. Okay. These two properties together show up quite a bit as we look at more and more stuff in your mathematical career. Essentially, this one almost looks like a distributive property, right? It's like the d over dx gets multiplied in times the f and times the g. It's not multiplication, right? You're taking the derivative of this thing and the derivative of that thing. But it kind of looks like a distributive property. And this one, it looks like you're just the multiplying by the k commutes. You can either do it on the inside or you can do it on the outside. These two properties together make the derivative operator a linear operator. That any operator that has these two properties is called a linear operator. And there's a bunch of them that we'll see as we learn more and more stuff. In fact, there's a whole course on linear things. It's called linear algebra. But anyway, there's these two properties. How do these help us? For instance, I know, here we go, here's some examples. I know that the derivative of x squared is 2x to the first power. So now I know that if I have f of x, come on now, if I have f of x equals 4x squared, then f prime of x is equal to the multiplying by 4. This is property 1 up here. Multiplying by 4 just comes along for the ride. So this should be 4 times the derivative of x squared. So that's 4 times 2x, which is just 8x. The result is the 2 just gets multiplied by the 4 to give you the 8, and then you get x to the first power. Another example here of that first property. If I've got the derivative of 7x to the 4, that's going to be 7 times 4x cubed, or 28x cubed. An example of this, the second property, if you have the, let's say f of x equals x squared plus x cubed, then the derivative of a sum is the sum of the derivatives. So take the derivative of the first part plus the derivative of the second part. In this way, we can do any polynomial really easily. If I've got, some polynomial like 7x cubed plus 2x minus, 2x squared minus 3x plus 5, I can do the following. I'm going to be a little careful here with this minus sign, although later I don't need to be quite so careful. But f prime of x says this should be the derivative of the first one here, 21x squared, plus the derivative of the second part here. Actually, I'm going to write an extra step down here. Let's write this as 7 times 3x squared, and this is 2 times 2x, and this is minus 3, right? The derivative of negative 3x is minus 3, and then there's a plus 0. One of the things, before I finish this, one of the things that both of these properties together do for us is that although I say the derivative of the sum is the sum of the derivatives, it's also the case that the derivative of a difference is the difference of the derivatives. If this is a minus sign in here, then this would be a minus. But I can see that because a difference is just adding a negative. And so if there was a negative here, I could think of that as the negative going with the g. But then the negative is just multiplying by -1, and then multiplying by -1 can be pulled out in front here. And so whether it's a sum or a difference, this is going to work because you have that property as well. Okay. So anyway, the derivative of that 5 was 0, and we get a grand total of 21x squared plus 4x minus 3. Right? So taking derivatives of polynomials turns out to be really pretty slick, because we have those two nice properties. In fact, those properties are going to be nice for us, not just with polynomials, but with just about anything we do. So there's polynomials. We'll come back with some other functions here in the next videos.